Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture Lecture Series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. In 1989, I was in the news because I contributed the world's fastest computing to mathematical knowledge. That contribution changed the way mathematicians solve some of their most difficult problems. In their old way, the solution of the most difficult problem in computational mathematics was unsuccessfully tackled on the blackboard or one processor. In my new way, such problems are solved across up to 1 billion processors. I'm Philip Emeagwali. On July 4, 1989, I became the first person to cross the boundary of human knowledge of the world's fastest computing across the world's slowest processors. Those processors encircled a hyperglobe in the 16th dimensional hyperspace and did so in the manner the internet encircles planet Earth. That was how I invented the first internet, that is a global network of 65,536 processors. What is Philip Emeagwali known for? I discovered how to combine computers into a supercomputer that's an internet. That discovery is like a light from an ancient sky. I'm the only father of the internet that invented an internet. The supercomputer of today is radically different from those of the 1980s and earlier. Back then, supercomputers were powered by only one processor. Each was the size of a refrigerator, and it cost up to $40 million each. The world's fastest computer of today can be powered by up to 1 billion processors. It occupies the footprint of a football field, and it costs 40% more than the mile-long Second Niger Bridge in Nigeria. I invented the world's fastest computing as we know it today. In 1989, I was in the news for discovering that the slowest processors could be used to solve the biggest problems and find their answers at the fastest speeds. The fastest computer is why you know the weather before going outside. The reason I was in the news for my contributions to fastest computing was this. I discovered that some compute-intensive problems that were impossible to solve with one processor could be solved across an ensemble of 1 billion processors. That's how the supercomputer is used to track how the coronavirus disease spreads. That was the audacity of my world's fastest computing that occurred on July 4, 1989, and that made the news headlines. The inspiration that led to my scientific discovery of how and why using 1,000 processors makes the new supercomputer the fastest came from my mathematical investigations of the rates of error growths that occur while solving the largest systems of equations in algebra. Error growths occur while executing the most compute-intensive set of floating point operations of arithmetic. Floating point operations arose from finite difference equations of computational linear algebra. Finite difference approximations arose from discrete approximations of partial differential equations that govern initial boundary value problems arising at the frontier of calculus. My inspiration to compute at the fastest recorded speeds arose from the need to execute the most compute-intensive mathematical operations. Such operations arose from the need to solve the largest system of equations of algebra. Such large-scale algebra arose from the need to discretize the partial differential equation at the frontier of calculus. Such abstract calculus arose from the need to encode some laws of physics and chemistry that govern the 20 most difficult problems in supercomputing. The poster child of the most difficult problems in supercomputing is the extreme scaled computational fluid dynamics codes that must be used to simulate the spread of a once-in-a-century global pandemic. The supercomputer must be used to simulate the spread of virus droplets among the billions upon billions of train passengers around the world that are packed like sardines. The fastest computer is used to simulate ways of stopping the spread of contagious viruses. The world's fastest computer is used to solve unsolved problems that are important to society. I began supercomputing on June 20, 1974 in Corvallis, Oregon, USA. At that time, I described myself as a mathematician who is a number theorist. My high-performance computing started as a hobby, not a serious profession. Back in Onitsha, Nigeria of the early 1970s, I conducted independent research on Pythagorean triplets. Each triplet was an integer solution of the equation a squared plus b squared equals c squared. In the 1970s, I gradually shifted my research interest from number theory of pure mathematics to numerical analysis of applied mathematics to large-scale computational fluid dynamics, and finally to massively parallel supercomputing that's executed across up to 1 billion processors. I visualized my 65,536 processors as encircling a hypersphere in 16-dimensional hyperspace and encircling it in the manner the internet encircles the earth. The mathematical fields of number theory and numerical analysis are almost diametrically opposite. Number theory is abstract and is investigated on the blackboard. On the other hand, numerical analysis is applied and investigated on the motherboard. Number theory demands precise solutions and is used to invent encryption algorithms. In contrast, numerical analysis accepts approximate solutions of partial difference equations arising in computational physics. Since the equivalence theorem was discovered in 1954, research computational mathematicians investigating the discrete solutions of partial differential equations indirectly prove convergence, and did so by only proving consistency and stability. By convergence, I mean that as my grid spacing tends to 0, my solution of my system of partial difference equations converges to the exact solution of my system of partial differential equations that I discretized. In 1981, and a few years after, and in College Park, Maryland, I did extensive consistency and stability analysis. That is, I theoretically and experimentally investigated the rates of propagation of numerical errors that arise when the algebraic computations advance from one time step of finite difference approximations to the next time step. I knew in advance that my approximations to the originating partial differential equations are stable if and only if the errors introduced at any time step were not amplified at later time steps, but were reduced at subsequent time steps. In my stability proofs, I computed for the norms of the solution. The stability proof, the theoretical proof of the stability of finite difference approximations of real-world partial differential equations are impossible to prove. Instead, I proved the stability of a quote-unquote closed problem and then confirmed the stability of the complete partial difference approximations, and do so by coding and testing the numerical solutions. From my linearized stability analysis, I mathematically discovered that I'll do fewer computations if I started from first principles or start from the second law of motion in physics textbooks, and do so to rederive the governing system of coupled, nonlinear, time-dependent, three-dimensional, and state-of-the-art partial differential equations of calculus. Such equations govern the flows of crude oil, injected water, and natural gas that's often flowing up to 7.7 miles or 12.4 kilometers deep and across an oil-producing field that's about the size of Baltimore, Maryland. I mathematically discovered that when I include the temporal and the convective inertial forces, then the governing partial differential equations become hyperbolic rather than parabolic. From my linearized stability analysis, I mathematically discovered that I'll do fewer computations if the discretizations or reduction from infinite to finite of the governing system of partial differential equations to an approximating system of partial difference equations were explicit rather than implicit. In 1981, my big question was to figure out how to bypass the two vexing limits in physics and computer science that were known as Darcy's law and Amdahl's law, respectively. From my linearized stability analysis, I mathematically discovered how to bypass the constraint that was imposed by Darcy's law. That constraint limited the execution times of computational fluid dynamics codes that were governed by that Darcy's law and bypassed the perceived Amdahl's law limit of the maximum speed increase of a factor of 8. That was how I addressed the vexing limit of Darcy's law that could make my world's fastest computing less efficient and more compute intensive. That was how I addressed the vexing limit of Amdahl's law on the speedups across the millions of processors powering the world's fastest computer. From my linearized stability analysis, I learned that My diagonal system of equations of algebra arose from conditionally stable and explicit finite difference algorithms, while my tridiagonal system of equations of algebra arose from unconditionally stable implicit finite difference algorithms. In the practical terms of large-scale, high-performance supercomputing, implicit methods allowed larger time steps, which are more efficient, but implicit methods only allow sequential calculations, which are slower to compute. I discovered that implicit methods that yield a system of tridiagonal equations of algebra yield longer times to solution than explicit methods that yield a system of diagonal equations of algebra. I discovered that it's possible to solve the system of diagonal equations of algebra and solve them in parallel, or by solving them at once at 65,536 processors, or to at once solve the diagonal system and solve them across my new internet. I invented that new internet as my new global network of 65,536 processors that were identical and equal distances apart. As correctly explained in textbooks on computational linear algebra, it's impossible to directly reformulate a system of tridiagonal equations and reformulate that system into an equivalent diagonal system. That was my motivation for reformulating both systems of diagonal and tridiagonal equations, and reformulating them to solve the same initial boundary value problem, particularly those in large-scale, high-fidelity computational fluid dynamics, such as petroleum reservoir simulations. In the 1970s and 80s, my dream of discovering the world's fastest computing across the world's slowest processors was ridiculed as wonderfully useless. The reason I conducted my world's fastest computing research alone was because supercomputing across the slowest processors was mocked and dismissed as a vacuous gimmick. In the 1970s and 80s, the conventional wisdom in supercomputing was this: quote, solve one problem at a time and solve that problem as fast as possible, unquote. In an article dated September 2, 1985, the president of Cray Research Incorporated, the company that manufactured 7 intense supercomputers, described his company's attempt to harness 64 processors as quote unquote more than we bargained for. My mathematical quest began as an abstract speculation of a lone mathematician in 1974, Corvallis, Oregon, USA. That speculation was on the pure logic of differential calculus and in the compute intensiveness of large-scale algebra. The precondition to discovering my world's fastest computing was that I, first and foremost, also discover how to efficiently map my codes across up to 1 billion processors. My quest for the world's fastest computing continued as the rigorous analysis of 65,536 computer codes, which were developed with my one code to one processor mapping and correspondence. That mapping was to the as many processors that outlined and defined my new internet. That's a new global network of 65,536 536 processors, I invented how to make the otherwise impossible to solve possible to solve. Such mathematical problems arise when attempting to solve the largest systems of equations in the computational linear algebra of petroleum reservoir simulation. I discovered how to solve the most difficult problems arising in mathematical physics and solve them across the millions of processors that outline the fastest supercomputers. I invented how to solve the most compute-intensive problems in computational fluid dynamics and how to solve them across a new internet that's a new global network of 65,536 processors. I'm the mathematician who invented how to do more computations and do the most computations in 1 second on the supercomputer and do more computations than what every person on planet Earth can compute during every second of every day for 1 year. I did the impossible by reformulating my system of equations of computational linear algebra that were tridiagonal, that couldn't be solved in parallel or solved across an ensemble of billion processors. And by reformulating that system from the governing second law of motion in physics textbooks and the governing partial differential equations, or PDEs, of calculus that encoded that law, and discretizing and solving my system of PDEs as a system of diagonal equations of computational linear algebra that solves an equivalent problem that could now be solved in parallel. I didn't reformulate my system of equations directly. I reformulated them indirectly. My systems of diagonal and tridiagonal equations each arose from the same detailed petroleum reservoir model. To recover otherwise unrecoverable crude oil and natural gas only required that we use the laws of physics to simulate the petroleum reservoir. It didn't require that we solve a specific system of tridiagonal equations of algebra and solve it by or in itself. How did I invent 9 new partial differential equations of calculus and invent them from the second law of motion of physics that was discovered 3 centuries and 3 decades ago? To make such an invention demanded that I be a polymath, not a mathematician alone. The polymath, that's a triple threat in physics, mathematics, and computing, focuses on solving the most difficult problem in computational mathematics and solving it as a holistic whole. Often the mathematician is limited to only solving the algebra problem. Often the mathematician forgets that mathematics is a tool and a means to an end, not the end itself. That algebra problem was derived from the physics problem. I discovered a different path to simulating the motions of crude oil, injected water, and natural gas flowing up to 7.7 miles or 12.4 kilometers deep and across an oil-producing field that's often the size of Lagos, Nigeria. I discovered how to simulate the petroleum reservoir and do so a billion times faster, and by returning to first principles, which were the set of laws of physics and chemistry governing the motions of the crude oil, natural gas, and injected water flowing across reservoir rocks. I began from the top and from the second law of motion of physics, and did so to enable me to correctly rederive the governing system of 9 coupled, nonlinear, time-dependent, three-dimensional, and three-phased partial differential equations of calculus. My new governing system of partial differential equations is hyperbolic and represents a new paradigm in calculus. The old governing system of partial differential equations is parabolic and represents an old paradigm in calculus. My new governing system describes the three-dimensional motions of crude oil, injected water, and natural gas flowing across a highly anisotropic and heterogeneous oil field. The new system of coupled nonlinear 9 Philip Emeagwali equations describes the motions of fluids through an oil-producing field and along 3 spatial directions. By 1989, I had discretized those partial differential equations to yield a new system of 24 million diagonal equations instead of the old system of 24 million tridiagonal equations. Both were the longest systems of equations ever solved in algebra, and that is one of my contributions to how to solve the largest systems of equations of computational linear algebra from petroleum reservoir simulation, and how to solve them across a new internet that's a global network of processors that were coupled and that shared nothing. Since June 20, 1974, in Corvallis, Oregon, USA, my quest for the world's fastest computing was to invent how to solve the most compute-intensive problems in linear algebra. I invented how to solve them across a new internet, and I invented that new internet as a new global network of processors that were identical and that I visualized as equal distances apart. Since the late 1940s, the method of choice among computational mathematicians that try to solve the most difficult problems in subsurface geophysical fluid dynamics was called the alternating direction implicit method, or the ADI method. The ADI method was used to discretize a system of coupled, nonlinear, time-dependent, and 2 or 3-dimensional partial differential equations. Such equations were classified as parabolic. They govern the subterranean flows of crude oil, injected water, and natural gas. In the 1950s, 60s, and 70s, the alternating direction implicit method was widely used to formulate a set of systems of tridiagonal equations that arise from finite difference discretizations of the system of partial differential equations that governs the subsurface motions of fluids flowing up to 7.7 miles or 12.4 kilometers deep below the surface of the Earth. In 1981, I discovered that it will be impossible to solve in parallel a system of tridiagonal equations in large-scale algebra and solve that system by dividing it up to 1 billion lesser challenging problems that in turn could then be solved with a one problem to one processor mapping and correspondence. and solved at once and across an ensemble of up to 1 billion processors. I discovered that it will be impossible to solve a system of tridiagonal equations and solve it by synchronously emailing equal-sized subsystems of that system and emailing my subsystems across my 1,048,576 bidirectional regular and short email wires. Likewise, I visualize those email wires as being equal distances apart. Furthermore, I visualize my email wires as marrying my global network of the slowest 65,536 processors in the world, and doing so to emulate one seamless, coherent, and gigantic super-fast processor that's a virtual supercomputer. As the lone programmer of my virtual supercomputer, I visualize those processors as married together as one coherent unit. That's not a supercomputer by itself, but that's a new internet de facto. I discovered that it will be impossible to evenly distribute equal subsystems of my system of tridiagonal equations and distribute those subsystems across each of my 65,536 identical and coupled processors. Each processor operated its operating system and had its dedicated memory. Because it's impossible to solve a system of tridiagonal equations and solve it in parallel, I formulated an equivalent system of 24 million diagonal equations that approximated a more accurate system of 9 new partial differential equations, which I invented, and that solves the same petroleum reservoir problem, or solves the same initial boundary value problem with different governing partial differential equations that differently encoded the same laws of physics that's at the physics core of the petroleum reservoir simulator. My mathematical beginning from a system of parabolic partial differential equations to inventing that system as a more accurate system of hyperbolic partial differential equations, and my formulation of a system of tridiagonal equations that approximated my parabolic partial differential equations, and my formulating of that system as a system of diagonal equations that approximated my hyperbolic partial differential equations, were mathematical inventions in calculus. That invention, or new mathematics, or my finite difference discretizations of the 9 Philip Emeagwali equations, changed the way we understand or solve the most compute-intensive problems that arise when simulating the flows of crude oil, injected water, and natural gas flowing across a highly anisotropic and heterogeneous producing oil field. A typical oil field is located 6,000 feet or 1.83 kilometers below the surface of the earth. But it can be up to 7.7 miles or 12.24 kilometers deep. My contributions to the physics used to pinpoint deposits of crude oil and natural gas were these. I discovered how to harness the millions of processors that power the world's fastest computer and how to use them as one coherent computing machinery that emulates the world's fastest processor, That's 1 million times faster than a single processor solving the same problem alone. The grand challenge of petroleum reservoir simulation was to compute the flows of crude oil and natural gas flowing from a water injection well to nearby producing wells. By making the news headlines back in 1989, my invention changed the way we execute the mathematical calculations in extreme scale computational physics. It changed how mathematicians solve the most compute-intensive initial boundary value mathematical problems, such as those arising in computational fluid dynamics. It changed how mathematicians solve them in parallel and solve them by distributing them across an ensemble of processors instead of solving them in sequence or solving them only within one isolated processor that's not a member of an ensemble of processors. My invention opened the door to how to solve the most compute-intensive mathematical problems and solve them across an ensemble of millions of processors and solve them when the governing system of equations of algebra had its non-zero entries only along its diagonal. My contributions to high-performance computational physics led to the discarding of the old way of solving the field's most difficult problems, to the new way of solving those problems across an ensemble of up to 1 billion processors. In the traditional way, physicists solve their toughest and their most compute-intensive initial boundary value problems in computational physics and solve them in sequence, or solved one problem at a time and solved that problem within one isolated processor that wasn't a member of an ensemble of processors that communicates and computes together, and do both as one seamless, coherent, and gigantic supercomputer. In my new way, mentioned in the June 20, 1990 issue of the Wall Street Journal and in cover stories of top mathematics news journals, I invented how to solve 65,536 initial boundary value problems of computational fluid dynamics, such as the detailed global climate modeling, and solved them at once. In 1989, I was in the news because I invented how to solve the most difficult problems arising in physics and mathematics and solve them in parallel. And I invented how to solve them across an ensemble of 65,536 coupled processors. My signature contribution to supercomputing is this: I put to rest the saying that the world's fastest computing across the world's slowest processors is a beautiful theory that lacked experimental confirmation. As a research supercomputer scientist who came of age in the 1970s and 80s and in the USA, the most important lesson that I learned was that you can't become a genius in supercomputing without foremost applying quote-unquote sitting power. I sat the longest in front of the massively parallel supercomputer of the 1980s that is in reality the supercomputer of today. That's the reason my lectures or my contributions to computing, mathematics, and physics are by far the most extensive ever posted on YouTube. The reason I could post my 1,000 video lectures on YouTube was that I sat longer than any supercomputer scientist ever sat in front of supercomputers. In the 1980s, I was the lone programmer of the precursor to the world's fastest computer. I applied the most sitting power upon the massively parallel supercomputer, and I applied that power more than any supercomputer scientist who ever lived. A violinist must practice daily. The violinist must go beyond reading her music on her way to Carnegie Hall, New York City. The violinist must apply her sitting power to get to Carnegie Hall. This important lesson of hard work, dedication, discipline, consistency, and practice applies to everything we do in life. You must play or think or dream soccer and do so every day before you can become a super eagle in the next World Cup. You must write daily before you can write your best-selling novel. Often, the best-known writers wrote 1 million unpublished words before they published their first 1,000 words. Since June 20, 1974, in Corvallis, Oregon, USA, I have written 1 million words on partial differential equations, finite difference algorithms, message passing codes, as well as lecture notes on my world's fastest computing that occurred on July 4, 1989 in Los Alamos, New Mexico, USA. In fact, the transcript of my 1,000 podcasts and YouTube videos is 1 million words long. These original podcasts and videos are what sets me apart from the likes of Albert Einstein. Supercomputer programmers believed my world's fastest computing across my ensemble of 65,536 processors. They've reconfirmed it across an ensemble of 10 million processors. People believe what they hear and saw and understand. As a black scientist who came of age in the 1970s, I was not welcomed to give public lectures in places like Ann Arbor, Michigan. For instance, I gave a job hiring lecture on the world's fastest computing on about September 24, 1985 in Ann Arbor, Michigan. The position was cancelled after the white scientific community discovered that I was black and African-born. The lectures that I shared on YouTube originated from the research that I conducted in the 1970s and 80s. People believe their eyes and ears. During the past 5 centuries, the leading figures in physics, such as Galileo Galilei, Isaac Newton, and Albert Einstein, presented public lectures on their contributions to physics that made each physicist the subject of school essays. I continued that 5-century-old tradition by posting 1,000 podcasts and videos, each on my contributions to physics, mathematics, and computer science. For comparison, the most prominent scientists of modern times only post about 10 videos on their quote-unquote original contributions to knowledge. This 100-fold gap between my podcast and videos and theirs is because my contributions is far more complicated and is normally executed by a 100-person research team. I have been supercomputing since Thursday, June 20, 1974. I began by programming one of the world's fastest computers at 1800 Southwest Campus Way, Corvallis, Oregon, USA. That supercomputer was rated as the world's fastest computer in December 1965. That supercomputer was the first to be rated at 1 million instructions per second. In the mid-1980s, I was the lone programmer of the precursor to the world's fastest computer that can solve up to 1 billion problems at once. I was the lone wolf at the unexplored territory of the world's fastest computing, where 64 binary thousand off-the-shelf processors can solve 65,536 problems at once, and do so after a one problem to one processor mapping and correspondence. Before I could parallel program each of my 2 raised to power 16 identical processors, and before I could compose their email primitives, and before I could send my codes to and from those 64 binary thousand processors and send them across 16 times to raise to power 16 regular short and equidistant email wires, I spent 16 years honing my craft, and doing so by building up my parallel programming muscles. In the 1970s and 80s, I built up my intellectual muscles in physics, calculus, and computing, and built them up in the manner I built up my physical muscles, and did so by playing tennis and lifting weights in the late afternoons. You become a runner by running daily. You become a writer by writing daily. I executed the world's fastest computing by supercomputing daily. I sat in front of the supercomputer for the 16 years onward of June 20, 1974 in Corvallis, Oregon. And before the Ann Arbor News of Michigan profiled me in an article that was titled Computer Wizard. That profile was dated April 26, 1990. So it took me 16 years to become a genius. For that reason, nobody was able to devote 16 years to exactly replicate my experiments that yielded the world's fastest computing. Being ranked as the greatest computer genius is like being ranked as the greatest soccer player. You also have to play soccer for 16 years before being voted as the world's #1 soccer player. Back in 1989 in Ann Arbor, Michigan, I was the only famous scientist and the only inventor whose name and contributions were discussed on the record by the members of the Michigan House of Representatives. To this day, I am the only inventor from Michigan, or rather in the world, that posted 1,000 podcasts and videos on these contributions to physics, mathematics, and computing. My lectures are on YouTube, Spotify, and Google Podcasts. Quite often, those reviewing my contributions to mathematics cannot scribble the 9 Philip Emeagwali equations. It's like someone who had never played a game of soccer giving advice to the central defender of Nigeria's Super Eagles. The reason I alone could post 1,000 YouTube videos was that I had 50 years of supercomputing behind those videos. Back in June 1974 in Oregon, I dreaded the supercomputer. But after 16 years, I won the highest prize in supercomputing. Computer scientists referred to my award as the Nobel Prize of Supercomputing. The genius is the below average person that worked hard to become above average. I built up my supercomputing muscles by coding in the mornings and coding supercomputers during the 16 years that followed June 20, 1974. Even on the days I don't have access to a supercomputer, I developed my algorithms and code fragments and wrote them in my parallel programmer notebooks. Or I researched linearized stability analysis of finite difference approximations of partial differential equations. My stability analyses were my a priori theoretical investigations of the exponential growth in mathematical errors, as well as sensitive dependence on initial conditions for my governing system of partial differential equations. Those equations and their discrete approximations are akin to the ones that define the initial boundary value problems which I solved across my new global network of 64 binary thousand processors that defined my new internet. It was after 5 decades of supercomputing that I became comfortable with the title, quote unquote, supercomputer scientist. I'm the subject of school essays for my contributions to the development of the computer. My contribution was that I discovered how to execute the world's fastest computing and do so across the world's slowest processors. My invention is a milestone in physics, mathematics, and computer science. The fastest computer in the world is the heavyweight champion of the computer world. In 1989, I was in the news because I discovered why and how a million or a billion of the slowest processors in the world could be harnessed and used to create the fastest computer in the world that's used to solve many problems at once instead of solving only one problem at a time. The world's fastest computer, powered by 1 billion processors, is to be what the violin is to the violinist. I've been practicing the craft of programming supercomputers and doing so since June 20, 1974 in Corvallis, Oregon. After half a century of supercomputing, describing Philip Emeagwali as an overnight supercomputer wizard is like describing a man born on June 20, 1974 as a young boy. A student writing an inventor biography report on my discovery of the fastest computing asked me, what course can I study to become the greatest computer genius? That's like asking what book to read to become the greatest violinist or the greatest airplane pilot or the greatest soccer player or the best climber of Mount Everest. When I was coming of age in the 1970s and 80s, the world's fastest computing across the world's slowest processors was mocked, ridiculed, and dismissed as science fiction. Since June 20, 1974, my grand challenge was to turn that fiction to actuality. Back then, asking a computer scientist to utilize 1 billion processors and use them to solve the most compute-intensive problems, such as the most detailed global climate modeling, was like asking a man who had never climbed a mountain to climb Mount Everest. Once upon a time, and in New York City, a young violinist asked a taxi driver, "How do I get to Carnegie Hall?" The taxi driver replied, "Practice, practice, practice." To become the greatest computer scientist requires that you make the greatest contribution to the development of the computer. And that greatest contribution is to discover a never-before-seen parallel and or quantum computing way of making computers faster and making supercomputers fastest, and to experimentally do both by recording a never-before-seen supercomputer speed increase and using all that speed to solve the world's biggest problems. That supercomputer speed increase must make the news headlines and must forever change the way we look at the world's fastest computer. I'm Philip Emeagwali. Thank you very much. Thank you. Thank you.
Insightful and brilliant lecture.